pleasure to introduce Michael Wehner. He's a senior staff scientist in the Computational Research Division at Lawrence Berkeley National Lab. His bachelor degree is in physics from the University of Delaware. His PhD is in nuclear engineering from the University of Wisconsin-Madison. And in our conversation this afternoon, I found out that, in fact, I did see, or likely saw, Cherenkov radiation in the small reactor at University of Wisconsin back when I was a kid. His research concerns the behavior of extreme weather events in a changing climate. Before joining LBL, he was a physicist in the first in the nuclear weapons division, but then in climate modeling group at Lawrence Livermore National Lab. His work now is in high performance computing, basically using that to quantify high resolution climate models. In fact, we were just talking about this image on his first slide, which I'm sure he'll go into. He was the lead author of the 3rd U.S. National Climate Assessment Report and of the 5th assessment report of the International Panel on Climate Change, the IPCC. Very prestigious, and he is a very important scientist with some wonderful work. Let's welcome Dr. Michael Wehner.
So thank you. From the introduction, you could tell that I've had a rather long and interesting career in a lot of different things, and so that's part of what physicists do, is find interesting things to do. Sometimes they're not what you went to school for, and everything I talk to you today is not what I went to school for, but that's okay because I'm a physicist. So I also need to have a disclaimer. This is one of the last things that Secretary Ernie Moniz did in the Obama administration was implement a scientific integrity policy. The way I read this is they can't tell me what to say, and I can't represent policy. So what I'm going to say today are my opinions and not that of the Lawrence Berkeley National Laboratory, the University of California, or the United States Department of Energy. So what do you hear a lot about climate, and we're going to go into some of that today. You might have different ideas of what climate is. I like this quote: "Climate is what you expect, weather is what you get." Now, I heard this given by Ed Lawrence, who you may not recognize that name as the father of modern chaos theory. He was a meteorologist by training. It's also been credited to Heinlein, the science fiction author. I'm not sure who said it first, but I heard Ed say it, so I'm giving him the criterion. And I like this definition because climate is the statistical description of the weather, not just the average, but the extremes, the way it varies, all of that stuff is climate. But we live in the weather, which is, you could think of as noise of the climate system. Extreme weather is when that noise gets loud. So I wanted to know a little bit about what this lecture series with its interesting title is about. And so I went to the web, and there's a nice history of the lecture series. And I searched out all the climate-related talks I could find. I found 23. And there's some interesting names here. If I get it. I used to work for this guy, and I've worked with these three. Carl, right down the street, is one of the world's leading analysts of satellite data. You got a crank here. But the most interesting thing was, oh, I'm serious about that. The interesting thing here is the first one that I found in 1974, man's impact on the climate. Now, I don't know who Mr. Dwight Nicholson is or was, but I thought that the date on this is really interesting because I was in high school in 1974, not thinking about climate. Nobody I knew was. But here we are so many years later, and that's still a topic that's questioned. Come on, people. I think we know better than that. And so I'm going to talk a little bit about that. I wouldn't normally do that, but I think it's appropriate in the day, in this time and age where we are with an administration that is particularly hostile to the kinds of things that I'm going to say. And what I'm going to tell you now, this isn't rocket science. We've known about this a long time. In 1974, we had known physics for a long time. This guy, John Tyndall, wrote, and I love the way he writes it, John Tyndall measured the radiative properties of many gases, including oxygen and carbon dioxide and methane. These are sort of how well they absorb infrared radiation from low to high. And he wrote, the atmosphere admits the entrance of solar heat, but checks its exit. And the result is a tendency to accumulate heat at the surface of the planet. That's the greenhouse effect. So he knew about this in 1859. And then another fellow, Svante Arrhenius, wrote in 1896 that the doubling of carbon dioxide would raise surface temperatures by 5 to 6 degrees centigrade above the pre-industrial temperatures. He wrote that in 1896. Now, I was part of the Intergovernmental Panel on Climate Change. We call that statement now the equilibrium climate sensitivity. How much warmer would the climate be if you doubled it after it comes to equilibrium, which takes a long time. And we wrote that it was 2 to 6 degrees. Well, Arrhenius was right in the middle of that. You might have argued that we haven't learned a lot in 100 years. I would argue we have. We just haven't learned a lot about this. I mean, we kind of know what it is. It's in this, probably at the higher end of this range. The low end is actually pretty well known. The upper bound is a little less certain. So in 2007, the IPCC, wasn't part of this report, they wrote that warming is unequivocal. And if you look at this temperature graph of a graph of temperatures from 1860, the middle of the last century, or the 19th century rather, to about the time of this report, you can see there's a pretty clear increase in temperature. This is data from thermometers. If you go back to paleoclimate records, which is things like tree rings and corals and that kind of inferred temperatures, you go back, in this picture, 1,000 years, and you can see that in the Industrial Revolution, there's all of a sudden something rather remarkable happening with this sharp increase in our estimates of the global average surface air temperature. And that is, of course, coincident with massive increases in carbon dioxide and methane and nitrous oxide, which are the principal radiatively active gases that Tyndall measured, that turn on when we discovered we could burn coal and make steam engines. Now, this is just an argument that the temperature is going up and, oh wow, the composition of the atmosphere is changing as well. There's a whole lecture I could give on the attribution of that observed climate change to human activities. What I wanted to just go briefly mention is that there are many indicators of a warmer world. This is a picture we put in the third national assessment of just 10 examples. There are many things that have changed. Carl looked at this one, air temperature in the lower in the troposphere, the lower part of the atmosphere, and these tell a consistent story. Now, a lot of this work is done with comparing observations to climate models, and that's a big part of what I do. But recently, because the climate change that we've had is actually so much larger than when I started in this, when I made my career change 25 years ago, that you don't even need climate models anymore to make a convincing argument that there's that this is a human-introduced phenomenon. And so these three lines represent what we think the energy imbalance from different natural and human factors are at the top of the atmosphere. So this is volcanoes. This is some solar estimate. You might see some fine lines that show some departures from that at very short time scales. And then some estimate of the human contribution mainly through carbon dioxide. Now these were things that trace back to Tyndall and were recently validated by a young scientist, coincidentally at Berkeley lab, Dan Feldman, who basically validated these curves observationally. So now, as a rather graphic example of the attribution of climate change to humans, without any models, let's just think about linear regression. Maybe linear regression is your model. ends up not a fancy climate model running on the world's fastest computers, but some spreadsheet running on Excel. So this is the observed temperature increase. This is the best fit using those two curves for only the natural forcing, the sun and volcanoes. And you can see that it pretty much doesn't explain this last 30 years or so. And in fact, there's a residual from this linear regression that is remarkably coincident with our estimate of this fit is remarkably similar to the human forcing that I showed on the previous slide, or our estimate of human forcing. So imagine that we now allow the strength of the human component to be any arbitrary amount. Right now it's 0 in some units that my friend Miles Allen judiciously or probably injudiciously chose as a name. So this unit is 1/10 of a degree of the observed warming to date. Now I should add, there's been, in this curve is basically 1 degree of warming since the middle of the last century. So if we make this 1/10, it looks a little bit better fit. You know, we go up a little bit, you get to 8/10. It's actually the lowest residual left. I think it's one more. And so you go a little farther and the residual starts to increase. And so the argument is that just through a simple linear regression, that 80% of the 1 degree of observed warming since the pre-industrial era is due to humans. And that is principally the burning of fossil fuels and the emission of carbon dioxide, with some minor additions to, from methane and also from land use changes. Well, it's going to get a lot hotter if we continue, in any event, whether we continue on this current path that we're on, or even if we all of a sudden decided tomorrow that we would reduce our emissions to 0, which is probably not going to happen because of a lag in the oceans behind the equilibrium. I had mentioned the equilibrium takes a long time to get to, mainly because the oceans have such a long time scale. This is a projection from the 5th assessment report of the IPCC, and there's a jump in it because the number of models, this is using climate models, changes at 20, they didn't all run past 2100. But you can see this red curve, and the good news is we're almost on the red curve. We're a little bit above it. 10 years, we're about 1% above it. 10 years ago, we were 3% above it, so we're going in the right direction, I suppose. So it's not the worst case, it's the worst case that we considered in IPCC. And you can see at the end of this century, our best estimate, which is a solid line, is about 4 degrees centigrade warmer than the current temperatures, which is 1 degree warmer than the pre-industrial. And so this is a planet that no human has ever lived on. In fact, today's planet is probably, you're the first people to live on a planet that warm. But certainly by this time. And then you go out into further time periods, you know, you start seeing like 8 degrees, which is like 15 degrees Fahrenheit on the average temperature. And actually, over land, it's a little bit more than that because the oceans don't warm as much as the land. These other lines are alternative realities for, if any of these are, none of these are reality, but alternative futures. This one, RCP 2.6, this blue one, is the geoengineering solution. I call it the vacuum cleaner technology. It's where you invent some technology to extract carbon dioxide from the atmosphere. These don't exist at scale, but they could perhaps. And that's about a 2 degree warmer than pre-industrial world. Then these others are in between scenarios. The Paris Agreement talked about 1.5 degrees. The 1.5 degree target, in my opinion, is pretty much a pipe dream. It would require what one economist at a recent meeting that I went to recently described as a wartime economy, where the entire world would have to radically change the way their economies worked in order to achieve this. I think 2 degrees is probably also a pipe dream given the political realities of the day. But that's just my opinion. Here's some projections we made on these different plausible scenarios of the future just for the United States. I just show them just so you get some idea that it's not all uniform. This is what I call the no policy scenario, this 4-degree warmer world. And you can see that over the upper United States, it's closer to 6 degrees warmer locally. But in the geoengineering solution, it's still warmer, but it's just not so much as the no policy scenario. So we have choices, one of which is don't do much. That would be this. One is do a lot, and that would be that, or something in between. Or perhaps this might not be what happens if we don't do anything because, like I said, we're actually above this in terms of the cumulative carbon dioxide emissions that was assumed back in 2005 when this scenario of the future was developed. So now I want to get to the meat of this subject, which is extreme weather. And this is what meteorologists consider eye candy. This is Hurricane Katrina, one of the most interesting and dangerous storms of its class. This is an atmospheric river. All the big storms we've had this year in California have been so-called atmospheric rivers. Sometimes the forecasters call them the Pineapple Express because they pass over Hawaii oftentimes. They're characterized as warmer than the other kinds of storms that get here, and with copious amounts of water vapor transported from the tropics to the extratropics. The other kind of storm we get in California is similar to this. This is an East Coast version, but is the extratropical cyclones. These form typically off the Aleutian Low, which is a persistent low pressure system off the Aleutian Islands. Hence, these storms are colder. And so the big snowstorms often, where the better skiing would come off the Aleutian Low, like extratropical cyclones. And this storm is just one I put on for giggles because I experienced it. It was called, these are radar images at different times. And it's a remarkably coherent frontal system that knocked out power in 5 states. And I landed the day afterwards at Dulles and it was 102 in Baltimore that day and humid. It was a nasty day, but they didn't have power hardly anywhere, including the traffic lights, which made driving difficult. So extreme weather is interesting meteorologically because of those pictures that I just showed you from the physics. It's really interesting physics, but it's also interesting because this is where the weather really impacts people and ecosystems. And I put some examples: heat waves and cold snaps, droughts and floods, violent kind of storms like hurricanes, tornadoes, other kinds. There are other events as well. But these are the things that we have tried to be studying, have tried to study in our group and others around the world. But what makes an event extreme? Well, it depends on where you're coming from. I come from it as a statistician, and so I think of the tails. And so this little bit, the 99.9 percentile, that's the extreme part. As a statistician, that's sort of the way I want to think about it. But that's rather arbitrary. Why isn't 95% extreme? That's a value judgment that you may make for any number of reasons. Or you might actually take the viewpoint that anything that causes large socioeconomic costs is extreme. And so if you get into this field, you have to be very careful about what you mean by this word. As I mentioned, I like to come at this from a statistics point of view. And so I want to tell you how we deal with this in statistics. And so there's a theory that I was attracted to it because of its elegance, called generalized extreme value theory. And it's well suited for looking at distributions of annual or seasonal maximums of, say, the hottest day of the season or the hottest day of the year. That's called, the statisticians call that block maxima, because you define a block. A block is 90 days, take the hottest day. What's the distribution of those hottest days? It turns out that it's a generalized extreme value distribution. And from that, if we can calculate that distribution, we can calculate the return period, and I'll define that in a minute. But just keep that in the back of your mind. And so this distribution is a 3-parameter distribution. I'm going to show it on the next slide. The original formulation by the statisticians was a stationary theory. But of course, climate change means time dependence. And something that's happened in the last 6 or 8 years has been climate scientists figured out the statistics literature, and the statisticians had given us not 20 years ago, which is not really a long time from getting from math to applications. It took 80 years for chaos theory to do that. Using covariance. And I'm not going to talk about that, just to say that this has now enabled us to really reduce the statistical uncertainties because we don't have to make assumptions about stationarity any longer. So here's the distribution that one tries to fit, and there are a variety of methods to do that, which I won't go into. And it's a 3-parameter distribution. The first one is location and scale. And these two can be thought of as, it's not the same as the mean and the variance of in a Gaussian, but it's not unlike it either. And then there's this 3rd parameter called the shape, which determines what happens at the far end of this extreme value distribution. So the extremes of the extremes, as it were. And this distribution can be bounded, and most physical systems are bounded. The temperatures can't be 500 degrees on planet Earth. You could model the classic example is people's height. Nobody is 15 feet tall. And so there are bounds. These are reflected in this distribution. The limiting case that k is the shape parameter is 0 is the distribution goes to 0 at infinity instead of some finite number. And so then it's sort of like a Gaussian distribution, which does that same kind of behavior. So we can invert this and get the return value. What I want to define here is a return period. And so you know what this is already because you probably read about the 100-year flood on the Russian River, for instance. And that would be the value of the level of the river that you'd expect to happen on average in a stationary climate once every 100 years. That's not to say that it couldn't happen one year and then followed by the next. That's a low probability event, but it could happen. And so once we fit these parameters, we can invert this and we can calculate this return value for a specified period. So what I'm going to show you now is the first model result, which is a comparison of my observational estimate of the 20-year return value of the maximum daily precipitation in the winter. This should say winter somewhere. It doesn't, but it is. Oh yeah, there it is, winter. This is what I get from a gridded product that the NOAA agency provides. And so what we're saying here is that the biggest storm every 20 years is going to put something like 90 millimeters on the ground once every 20 years over that, on average, over the 50 years or so that this data set involves. Now here's some simulations of this quantity from 3 different climate model runs that I made. These 2 models, this is sort of the AR4, the 2007 resolution of climate models. A climate model takes the planet and divides it up into squares, and you map the relevant equations of motion and equations of radiation transport and moisture budgets, and et cetera, onto a grid, on the sphere. In this case, in this case, the grid was divided up into 200 kilometers on a side squares. That was the technology in 2007. The AR5, which was 2013 or 12 maybe, I forget, was half that. And what I've been doing at Berkeley Lab now is pushing this to 25 kilometers. So it's a much finer resolved picture of the planet. Now, to explain resolution in a more civilian way, I learned this when I was talking to journalists, is consider this as a TV, and this is your regular TV, and this is your 1080p, and this is 4K. And so as you get to finer and finer resolutions, it's a better picture. Similarly, a climate model has higher fidelity of the weather systems that are trying to simulate. And what happens is, when we go from the very coarse resolution to these very fine resolutions, the storms are more realistic. Particularly the extreme storms are more realistic.
Dr. Wehner?
Yeah.
I mean, I think this is amazing. That last one is climate models, and it's generating spots that do end up getting a deluge in the middle of Montana or Idaho there.
Yeah.
That
yeah.
you know, your earlier models didn't say that. We know the observations say, yeah, those places on the Earth get deluged by water every once in a while.
Yeah.
And your climate models are recovering that exact same thing. You'd say that's a place on the Earth that's going to have big.
When I first saw this, I was quite surprised myself. The reason for this is that one of the things we do, and I'll show this in a movie in a minute, is that we resolve the mountains a lot better. But we also resolve the frontal systems themselves, the weather itself, even out in the middle of the ocean where it's flat. I should add, this is sort of the weather forecasting technology of 15 to 20 years ago. And so climate models have caught up. Now weather models are considerably finer, but they've caught up to where forecast models were not very long ago. And so forecast models typically run 7 to 10 days integration. This was 27 years. It took a few months, but it is feasible. And the computer we now have at Berkeley Lab is the 5th fastest in the open world computer on the planet. And I can run this quite a bit faster, although I can't utilize the entire machine because the way the code is not particularly well written for such novel architectures as that one. So let's go to the movie. This is a view of the water vapor from the top of the atmosphere integrated down to the bottom. And when I first started looking at this is remarkable. It made hurricanes. No climate model above this resolution really makes them. And in fact, I'll show you in a minute, it does a pretty good job on it. One of the things to notice is you see how, besides the swirly hurricanes, you see how fine these excursions of extratropical moisture. These are atmospheric rivers. Now, how well defined they are. They're not fuzzy. They're actually sharply defined, like in real world. I'm going to stop this one. This is 200 kilometers, same model. And obviously there's no hurricanes, but also these frontal systems are much more diffuse. That's the big deal, is that the gradients of temperature and moisture are much sharper. And they're much sharper. It's not just the resolution, it's the way the equations of motion respond to that resolution. And so, so the good news is, maybe in the back they might look the same. You know, AR 4 and 5 were written on this, the natural climate assessments I wrote on this stuff. And you know, if you blur this out, it kind of looks like this. And so for statements about continental scale, annual average or seasonal average climate, this isn't a bad tool. But for extreme weather, where these gradients are not well simulated here, I really need a tool like this. And so that's where we're at, and it's pretty exciting. So, am I on the right one? Yeah, okay. So Moore's law is still alive and well. The largest computers continually get faster, usually by adding more processors. I only used 8,000 processors on a 120,000 processor machine. Now, I'm actually only using 3,500 on a 700,000 processor machine because the processors are vector chips, which, you know, if you're of a certain age, you'll know what that means. And, you know, it's running twice as, it's running 50% faster on half as many processors. And it typically took me about 3 months to get that one done. I'm running faster now. I don't know how much faster because I'm doing a lot more simulations all at once, and I haven't bothered to count. But here's a picture of how well it actually does. So this is an observed estimate of all the hurricanes from category 0 to category 5 on the Saffir-Simpson scale from this period, 1979 to 2005, that I simulated. And here's what the model did. And there's some obvious deficiencies, but also some strengths. Let me peel off the category 0s, the tropical storms. So this is just now category 1 through 5. And you can see now that one of the major bias is a word that climate modelers use in polite company. I like to call them errors. But the bias here is that we make too many in the middle of the Pacific. You might see some other ones. You might say, oh, they start too close to Africa. When I showed this to observationalists, they said, well, that might not be a problem because we actually don't always pick them up that early. The tracking of these data sets are done differently. These are done by hand because they happen in real time. We're running many, many times faster, 300 or 400 times faster than real time, and so we can't keep up by hand, and so we have to have an algorithm find it. That actually is an interesting computational exercise itself, and in fact, for those of you who are interested in machine learning, this is something I won't talk about, but it's something that my colleagues are applying to these data sets to find storms of this type and others. But so, yeah, we're picking them up a little bit better here because we have complete data in a model, whereas you don't have complete data for the real world. You're data limited.
Dr. Wehner, I mean, these are remarkable. I want to make sure I understand. Like, this is just putting forth, keeping track of water and temperature in a climate of the Earth. You're generating these extreme events happening in these locations because the model says this is ocean, this is land. If I have this humidity, it's going to be
indeed,
like this.
indeed.
It has nothing to do with like these are where they happen, and so you're to get it as close as this means that other than you looking for these subtle offsets, do you measure 20% too many, or is there an effect where people aren't finding them, as you said, off the coast of Africa? Or if I looked at this, I would say they should be looking to see if more are happening in the
well, it even gets better than that.
Oh, wow. Okay.
Because these are the category 4 and 5 storms. These are the intense hurricanes, the ones that I'm interested in because they're the ones that do all the damage. And this model makes more or less the right number, which is pretty remarkable. And so, yes, these are not wired in any similar way. These storms come out of thin numerical error, as it were. This is initialized in 1979. The chaos of the climate system, in this case just the atmosphere, has about 3 weeks of memory, so the initial conditions are lost. In fact, we discard the first year of simulation so that we are in this completely chaotic regime. So the point is this provides a tool for us to make statements. Oh, one last thing. This is a relationship between pressure and the maximum wind. The observations are in blue and the models in orange. So maximum pressure is, or minimum pressure is on the y-axis maximum wind speed. And so what this shows us is that the storms are actually fairly realistic, that you're producing minimum pressures in the centers of the storms and maximum wind speeds that are more or less the same. There's a little bit of an offset in the Pacific, but it's still, pretty remarkable. Now the number that it makes are pretty good. The observations are, over this period, were 87 per year globally, and the model made 84. This is from Cat 0 to Cat 5. If we went from Cat 1 through Category 5, it's about 50. And so, and that was actually another thing that I had no idea before I did these simulations that the model could do that. So this is a tool then that we can do climate change experiments with and say, okay, in one of these warmer worlds, how many hurricanes will there be? Now that's a really interesting question that's open to debate. My results suggest that there'll be fewer hurricanes. But all of the groups that can do this suggest that the most intense hurricanes increase in number and increase in intensity. We're currently drafting a paper that suggests that we need to add Category 6 and Category 7 to the Saffir-Simpson scale because we're rapidly approaching a world where these things will happen with some regularity. And so what I have here is a measure of the most intense storms in the simulation of, say, the present day, which is In this case, it was a little earlier, so it's only 0.85 warmer than the pre-industrial, versus 1.5. This was done to aid the IPCC in its request from the COP21. And then at 2 degrees, and so there's a difference between 1 and 2 degrees in the most intense storms. And then the 4 degrees of the RCP 8.5 is yet higher. And so in this reality of 4 degrees warmer, the number of category 6s that were in our calculation is substantial. In my colleagues' calculations at the Geophysical Fluid Dynamics Laboratory in Princeton, his would have a lot of category 7s in his simulation. And so as disturbing as these numbers might be, they are more conservative than my friends. So here's the last movie. This is an atmospheric river. This is a real atmospheric river. And what we're going to see now is a simulation. Again, now the color is the water vapor. These are winds. And then this color is the precipitation. And what I want you to see here is that when one of these rivers in this simulation hits the coast, most of the precipitation falls out along the leading edge of the mountains. And in fact, it's going to get real interesting right here. And so on this particular day in this simulation, it's really snowing probably like crazy on the western flank of the Sierras, which of course, if you've ever been there, you know that's what happens. And it doesn't snow so much in Reno. And this is another reason why we need to have these high resolution models, because the high resolution model represents the topography, the height of the mountains, much more realistically, because in the model, the height of the mountain is the average in that grid spacing that it's covering. And if that grid is 100 kilometers on a side, you hardly have any of the Sierras in it. Whereas at 25 kilometers, you're doing a decent, although not perfect job of representing the orography. And so if I were to make this movie, I haven't, at the 100 kilometer, this same kind of atmospheric river would not precipitate as much on the leading flank, and a lot of that moisture would run into the Great Basin. That's a clear error, I will say. And so what am I supposed to do with that when I'm making a projection of the future? It's not an easy thing to correct on a regional scale like that. So not only is extreme weather better simulated by this model, but regional climate changes as well. Let's see how am I doing on time. Okay. Extreme event attribution. Now my group is very small at Berkeley Lab, but one of our strengths is getting at this question of attribution. And when some big storm happens, or this year, the Oroville Dam storm, for instance, people want to know, climate change, is this climate change? And this attribution has become a bit of a cottage industry. In the Bulletin of the American Meteorological Society, now there's been 4 or 5 special supplements that have looked at individual events and said, okay, climate change was a factor, or climate change wasn't a factor. And so the most important thing I want you to take from this lecture is the following. It used to be said when there was a big event, quote, climate scientists won't say anything about individual events, but this is consistent with what they expect. That's no longer the case. There is much to be said about individual events. Not every individual event gets analyzed because it's difficult, but every event should have, if that's of any impact, should have an attribution statement made. Sometimes it will be that we find no human influence. But oftentimes, especially for heat waves, there's a strong influence. So we can't ask this question that we get asked by is this climate change? But there are 2 questions that we can get answers to. And one is, how has the risk of this event, of this particular magnitude, changed because of climate change, if at all? Or how did climate change affect the magnitude of this event? And so the 2 different ways, we call this one the probabilistic way of looking at it versus a mechanistic way. And so this is, if you fix the magnitude of the event, how did the probability of it change? If you fix the probability of this event, how did the magnitude change? And so the same question, just turned on the side. So we use the models to characterize these extreme events in the actual world as close as we can simulate it, and then compare it to a counterfactual world without, I should say without, I'm sorry, without human interference in the climate system. And so this is a heavily model-based activity. And it's important that one makes sure that the models are fit for purpose, which is why I showed you all this stuff about the high-resolution models. Because for certain kinds of storms, we really do need that. Or the models are not, quote, fit for purpose, and so you may get the wrong answer. And in fact, the literature has such examples in it. I'll show you one that we think we fixed. But consider 3 different summer heat wave events, which are amenable by these coarse AR5 type models. Europe in 2003 had a very hot summer. There were 70,000 excess deaths attributed to this event. That's a lot of people that died above what was expected for that period of time. Now, many of these people were elderly. You might argue, well, they were going to die 6 months later. But many of them were not. Many of them were young people. Children especially are vulnerable. So the human toll in this event is enormous. In Russia in 2010, the estimate was 50,000 excess deaths, compounded by massive fires that were due to some mismanagement of their fire prevention system and drainage of peat bogs and whatnot. That contributed to lung diseases, which added to the death toll. Or Texas in 2011, we don't have an estimate of how many people died. These places have socialized medicine, so it's easier to count than it is in the United States. So we don't know. But there were a lot of dead cows because the price of feed went so high that they went to market faster. The state of Texas estimated that should say $8 billion of damages to the state of Texas alone through the livestock industry. Now these are very rare events. What I want to talk to you now is about how the rarity of these events have changed. And so we calculate the change in risk, where risk is going to be defined in a minute, by comparing the extreme value statistics from these realistic simulations, the factual, to those counterfactuals. And we'll skip the statistical mumbo jumbo, although I love that part. This is the last equation. It's pretty simple. It's to define a measure to quantify the human influence on specific individual weather events. We call it the risk ratio, although you really probably should call it the probability ratio, because risk means different things to different audiences. And it's a probability of this event our estimate of the probability of this event in the real world versus our estimate in the counterfactual world without a human interference to the climate system. If this ratio is 1, if these probabilities are the same, we say there's no human influence. If this is 2, we'd say, well, humans doubled the chances of this. If it's 1.5, there's a half again chance increase. So for these 3 events, at the time they occurred, this risk ratio was about 2. Median estimate in the ones where we have nice Bayesian ranges encompasses 2. So climate change, our best estimate is that doubled the chances of reaching a magnitude that 70,000 people were killed in excess of what would normally be the case. Now we can put this into the future using our projections, and this slide was done in 2013, so the question was what happens in 10 years? And the different events respond differently. For the European event, it's 35 times more likely in what is that now, 6 years from now. And in fact, another event of this magnitude did occur in 2010 in Europe. Fewer people died because of the measures that were taken, the social measures that were taken in Europe after this first event. For instance, doctors in France are not all allowed to take vacations in August. You know, they put in practices, you know, and that's only one. There's many others to ensure that people can survive these kinds of events. And that's an important aspect of climate change, is how are we going to adapt to what looks to me to be inevitable. And so in fact, this Europe thing, this is our median estimate of the probability of this event. You can see that before 1990, it was a very rare event. You know, it's less than the thickness of this line on a 0 to 1, the probability. By 2040, our median estimate is that there's a 90% chance of this event happening. So 9 out of 10 summers in 2040 would be as hot as it was in 2003. And this is relatively insensitive to all these different scenarios I talked to at the beginning, because there's not a lot of difference before the middle of the century in these different scenarios because of the way the ocean responds. Now, this is an event that was really interesting, the 2013 Colorado floods. 10 people died. 19,000 homes were destroyed. It's a $2 billion event. It was a very unusual event. We didn't make an estimate of its return period, but others did, that at some places it was as high as 1 in 1,000 years, although that number is very, very, very strongly debated. This was an event where not only can you not use a coarse model, but you can't actually use a long model either, because the large-scale meteorology that caused this event is so rare that we actually had to use a forecast model. We call it a hindcast because we ran it after the event, where we wired in the large-scale meteorology. This was not uncontroversial, and it took us a long time to get this published, but it is now in press. And what we found is we looked at it, we did an ensemble of simulations, so we did many simulations with different initial conditions, perturbed like a weather forecast would be. And we find two different distributions. I hope you can see them. The blue is the world that was, the hindcast, or that was. And the green distribution is the hindcast that might have been, had humans done their thing. And we found that there was a 30% increase in the amount of precipitation. So this is a mechanistic, remember my slide there about the different ways of answering this question, that there's 30% more precipitation. And this actually then has interesting repercussions. If your house was in the floodplain or outside of the floodplain of this counterfactual world, but inside the factual, you might say, well, climate change flooded my house. And you'd have some reason to say that. Now, one of the things that was difficult about this result is I didn't expect it to be 15%. I expected it, or 30%. I expected it to be 15% because of some relationship. Now, this is physics again, the Clausius-Clapeyron relationship, which is a relationship that tells you what the saturation, what the amount of water in a column of air that's fully saturated can be. It scales at about 7% per degree centigrade. So if you have 2 degrees of warming, you say, 15%. But we found 30. And so what was going on, and this is what made this paper difficult to write, because I actually thought the wrong thing. I thought that the winds were stronger and driving things up the mountains harder. But my young colleague, Pardeep Paul, didn't believe me and was strong-willed enough to tell the senior scientist that he's wrong, and he was. And instead, what happened is that there's actually more convective activity. And so the storm was more violent locally. And that was what was driving the wind. So I had it backwards. I thought the winds were driving it, instead driving more precipitation. But no, it was more precipitation was driving the increase in winds. And so this is one of those interesting things that, you know, it's not always what it appears to be. And it's important to stick to your guns and show those old guys they're wrong. So final example is a paper I wrote last year. I was traveling. I travel a lot. I was traveling in Europe, and I was in Prague, and the only thing on TV that I could understand was the news. And this was during the Pakistani heat wave. And I was touched because people were dying. People were dying so fast, they couldn't bury them fast enough. It's a Muslim country. They have to bury within 3 days, I think. And they showed a story of a father who had lost his children. And, you know, given my group's expertise, I went back and said, you know, what can we say about this storm? Or this heat wave, rather. It turned out to be a very interesting heat wave, and it turned out what I didn't know is that a few weeks before, there had been a similar deadly heat wave in India. And so the first question was, are these related? And the answer is, meteorologically, no. They were 5 weeks apart. The chaos of the system is completely different. In fact, the Indian one in late May was a hot, dry event associated with a delay to the onset of the monsoon. When the rains come, it cools things down. And so this is the plot of relative humidity on the y-axis and temperature on the x-axis. It's a scatter plot of all the data I could find at Hyderabad, which is a town in the middle of this heat wave. And the black dots are the actual days during the event itself. And you can see that they generally tend to be very hot, and the hottest days tend to be pretty dry, like 20% relative humidity. When I look at the Karachi event, I find something very different. Now, the climatology is different there. It's a coastal city. Hyderabad's inland. And it's generally more humid, but this particular heat wave was very humid. And so some of these hottest days were 40% humidity, and some of the other ones were 60% humidity. Now, the colors are representing a field called the heat index, which is sort of like the opposite of the wind chill. It's how hot did it feel, and it's an empirical model, a bicubic formulation of relative humidity and temperature that is supposed to represent how hot it feels like, and so it's higher on a humid day for the same temperature. And it turned out that this heat wave that killed so many people in Pakistan was particularly humid. It wasn't actually that hot, but the combination was a very rare event. And so I did the simulations again, in this case finding a shift from the actual, the reds, from the blues that's substantial for both these. These are formulated in the heat index rather than in temperature itself. And I found that this risk ratio, this change in the probability of the event, was 30 for India. In the paper for Pakistan, I wrote it was greater than 1,000. The actual number was 10,000, which is not infinity. It could be infinity. And in fact, as we get into warmer and warmer worlds, we will see risk ratios that our low estimate is, and we try to do these at a range, is infinity. And what that means is that the event was impossible prior in the pre-industrial world. And as this distribution of temperature shifts, and I predict we'll see it first in temperature, is that there would be events that we think where we go back to that original question, is this climate change? And the answer will be yes. That has not happened yet. All events that we've analyzed so far had a non-zero estimate of the pre-industrialized probability of its occurrence. But in this case, it was very, very small. I published this in that in the BAM supplement. This is all online and free. So to conclude, the risk of extreme weather has already changed, and in some cases already changed very substantially, and attributable rather directly to fossil fuel burning. High performance computing is, I believe, critical to our understanding of how much it changes, and for that matter, what the relevant physics are. Why do we get better than the thermodynamics, for instance? Why do we get higher than, it's not better, higher than the thermodynamics in the Colorado flood? I mean, that was something that was enabled only by the high performance computing capabilities we happen to have, lucky to have at Berkeley. So, I'd like to leave you with this question. What is dangerous climate change? Presumably it's determined by the impacts. Now, lots of old people died in these, lots of young people died. It was my child or my grandmother that died in these events. I think that's pretty dangerous. There's often espoused 2-degree target of safe climate change. I think it's fundamentally misleading because dangerous climate change is already here. And so to talk about safe amounts of climate change is safe to whom? And I think that's a question that I can't answer. I think everybody has to answer that. I can't answer it for you. I can answer it for myself. And I think you have to answer it for yourself. So thank you. Feel free to email me or ask questions now. Here's some further resources on climate science. I particularly like this one. This came out of, hopefully it'll live for a while longer. This came out of the third National Climate Assessment. They took the assessment report and they made it much more approachable by putting it on the internet in a way that the authors could not do. So, and that's my email here at the end. Well, thank you.
Thanks. Let's take a couple of questions. Yes, Jim.
You were consistently describing like the effect in terms of mortality and listing numbers of people who might have died as a result of an extreme weather phenomenon. Some of your earlier slides, I was looking at the weather changing like through the Midwest and wondering what is that going to do to agriculture? I'm thinking of growing corn and
oh yeah, yeah.
And you increase by several degrees. What happens?
So you hit upon something close to my heart. I've been trying to work closely with the University of California at Berkeley, and I have an office now at the College of Natural Resources, and my office mate is an agricultural economist. And it's a perfect match, because what do farmers care about? Temperature and rain. What do climate scientists do? Temperature and rain. So it's a good match. And it's very disturbing. A drought in Iowa would have global repercussions on the agricultural economy. In fact, there's some evidence this has already happened. There are folks, and I can't defend or not defend, I'll just explain, that believe that the Arab Spring had some attributable to climate change cause. And the logic goes as this. There was a crop failure in China. China went on the market. They bought up a lot of grain. It raised the prices of basic foodstuffs. Who are most impacted by increases in basic food prices? It's the poor, because the poor spend more money on more bigger fraction of their income on food than on anything else. So the argument is that you had people that were already pretty unhappy, and now they're hungry. And so the same argument is given for Syria as well. But it's a complicated argument, the link between climate change and human conflict. It's usually not the cause, but it certainly could be through this global agricultural economy, a compounding factor to conflict. So yes, and it is serious. There are some studies. There's a very interesting paper by Wolfram Schlenker in the Proceedings of the National Academy that looked at corn price volatility as a function of temperature. Turns out that corn yields go up slightly as temperature goes up, and then they fall off a cliff. And so as you get warmer, that threshold becomes more and more frequent. And so then the question is, can the seed companies genetically engineer corn to tolerate such temperatures? And the answer is not at all clear that to maintain current yield is probably unlikely.
Well, we have the room until 5:15. I'd like to suggest that those of you who need to leave because it's 5 o'clock, please do so quickly and quietly in the next 1 minute, 90 seconds, let's say. And the rest of us will stay for a continuation of the question and answer session.
And thank you all for coming.
No. You want a stamp?
Good, I had no idea what you were asking. Yeah.
Earlier we were talking about hurricanes and how their intensity can increase, but then you were saying that you thought that they would stop.
No, the total number goes down because there are fewer weak ones. But the intense storms become more intense, and there are more of them that reach the level that we call intense.
Okay.
But it's a complicated question. So you have a distribution of wind speeds, and it's changing in two ways. It's changing at the low end and the high end.
So let's take this to the whole group now. The question was about the number of
hurricanes in
total
a
hurricanes
warmer
going down,
world.
but you were basically saying all the ones that were extreme are going to go up.
So the simulations suggest that the total number of storms goes down, and most storms are weak, and And like I said, the most intense storms get more intense, and above that category 4 threshold, there are more of them. So why would there be fewer weak storms in a warmer world? And in fact, when we look at other types of storms, we've looked at extratropical cyclones in a wide variety of different models, and it does look like that in a warmer world there'll be fewer of that category of storm as well as a shift in their location closer to the pole, so that the storm tracks will migrate northward, which has serious implications for California. And we could talk about that if you like. But the reason my theory on why there are fewer storms of this kind is that a warmer atmosphere is more stable. It's more stable in two ways. It's more stable in the difference between the equator temperatures and the pole temperature. So this equator to pole temperature gradient, which is reasonably high now, becomes decreased. And in fact, there's some paleo evidence that some zillion years ago, the planet was more or less isothermal. And there are fossil evidence of dinosaurs above the Arctic Circle, which is another interesting question. But the other way the atmosphere becomes more stable is what they call the lapse rate, which is the profile of temperature in the vertical dimension. And that flattens out as well. And so these gradients are what drive weather. And so if they tend to relax, then there's less noise, and so less weather, as it were. But that's more, I would call that some of Mike's idle speculations, and I haven't written about it yet.
That was my exact question. What are your projections for extreme weather? Have you started with the Bay Area and expanding all the way to California?
Well, yeah, I should have shown this picture. It's not really extreme weather, but it's a picture that I'm putting. I have a deadline on Friday for something called the Climate Science Special Report, which is a prelude to the 4th National Climate Assessment. And one of the pictures I took was from a graduate student, a new PhD from University of California, Davis, who did a whole lot of simulations of the Sierra snowpack using a whole bunch of high-resolution models, different ones, including mine. I didn't have the best one. But he took the best one, and then he made a projection of the end of the century. What happens to the snowpack? Well, it's basically gone. 95% of the Sierra, what would be the current Sierra snowpack, would not be snow any longer. It would fall as rain. Over the western United States as a whole, it was about 35% is gone. Only at the highest elevations would there still be snow cover. And so that has really serious implications for California's hydrology. We have this engineered system of dams and canals and levees that moves water from the Sierra at the right time to our very efficient agricultural system. That's efficient because you put water on the crops at the right time, because it doesn't rain much in summer. You put the water on when the crops want it rather than waiting for the weather. So it's better than nature in many ways. But that's going to be interfered with if we no longer have the infrastructure that's enabled by this reservoir of snowpack. And so I think that's a very interesting policy relevant question that this state needs to address. Yes, please.
Is there a climate change cutoff point at which point the max it can reach and then everything will just?
That's an interesting question. What happens if you burn all the oil, all the gas, all the coal, and all the coal tar sands? It's in the ground. If you leave it there, it's what they call a stranded resource. I'm not sure there is such a thing as a stranded resource. The inclination is to make some money. You're going to pull it out. The answer, I think, the short answer is nobody knows. There were some papers written by Jim Hansen, who's arguably the most famous living climate scientist, that said, "Oh, we'll have runaway Venus," and he wrote those papers because the model blew up. It just went unstable. I don't believe any of that. And so I asked others, what's going on here, and at very high atmospheric concentrations of CO2. So we're at 400 parts per million now. I think we're looking at 1,100 in the latter of these things. You know, let's say we went to 2,000 or 3,000 parts per million. There is, like I said, there's some fossil evidence that we've had those kinds of concentrations in the very, very, very distant past. The planet became isothermal in that the equator temperatures and the pole temperatures were more or less the same. That's kind of like Venus is, but Venus is way hotter. What happens in an isothermal planet? Interesting. The winds die down. If the winds die down, then the ocean circulation dies down. Then the ocean stratifies and becomes anoxic at depth, and everything dies. And so, in Hansen's doomsday scenario, I don't think we all cook, we all starve. And so, because if the ocean has no biology, and we kind of cooked. But it's an interesting question. It hasn't been looked at anywhere near in depth, these very high concentration things. The assumption, I think most climate scientists would like to believe that at some point in time people start believing us and actually do something about it. But of course there's little to no evidence that that is going to happen. I don't have a good human model. Please.
Yeah. I have a question about the accuracy of ability to use the models to predict the future. You showed really interesting data about how you test your models against actual data, during periods when things actually happen. But you also have a lot of change going on that's pretty unusual.
Oh yeah,
So,
yeah.
Is it like you can do a delta calculation over a region and add some extra feature to see what would happen? But what about how do you feel about the accuracy of the predictions?
So there are many sources of uncertainty. There is and they evolve over time. So in the short period of time, the biggest source of uncertainty is initial conditions. As you go over time, that doesn't matter so much. In the middle, the biggest uncertainty is the model range. The differences in climate sensitivity. But in the distance, in this distant future, the biggest real uncertainty is what people will do. So now you asked what is really a fundamental question. The group I used to be in at Livermore was called the Program for Climate Model Diagnostics and Air Comparison, and it was focused on this question of what are the model errors and what are they attributable to, and how can they be fixed? And so what we typically do is we look at the past and we try to simulate the past as well as we can. And there are quite serious glaring deficiencies. I showed only one, and that's my hurricanes in the middle of the Pacific. But there are lots of other things where you could argue that the model isn't fit for purpose for making projections or attributions or whatnot. But I think the most compelling argument for why we should believe this stuff is that go back into the literature and look at projections made 20 years ago. And where are they? And in fact, there are two sets of projections that are interesting to look at. One was written by Miles Allen in 2000, well actually 1999, between Christmas and New Year's. His wife wasn't real happy about that as he was working. But that paper, and then an earlier one by Manabi and Stouffer at Princeton, where they made projections out into the 21st century, and so you can read the line and say, okay, this is 20 years later. Where are they? They're right, spot on in the middle of the uncertainty. So one has to embrace the uncertainty and say, okay, this is our range.
But they didn't have the tools that you have.
They didn't have that's the remarkable thing is those tools were remarkably crude, and they still made a projection that was fundamentally sound.
So there were a lot of other people that made predictions that were not? That came at that time?
No, there really weren't. I mean, one of the lectures here, and it would be interesting to go watch it. One of the lectures in the series, where is it now? Is the beginning of the climate field in the 1970s.
That's me.
Did you give this lecture?
Oh, yeah. They weren't.
Yeah, there weren't that many people in the 70s
I know.
doing this kind of work.
I'm the last man standing.
There you have it. And so, you know, that's great that it's you, actually. So, you know, there's a lot more activity now, of course. You know, and I think not every projection is going to be correct, but I'm sure that these global mean temperature things, not that one. This kind of projection, that's just energy balance at this point. There was a question in the back somewhere.
Yeah. So sorry to backtrack so far, but at one point you showed a graph of the rising temperature after the Industrial Revolution, and at some point in there was like a drop in temperature rather than a rise in temperature. Was there any explanation, like after the Industrial Revolution? Is there any explanation for that?
You're talking about
The one at the bottom.
this one here?
Yeah, that one.
Yes.
Yeah, okay. Well, I wish I had another slide that went all the way out to 2016. I wrote a paper in 2008 with Dave Easterling at NOAA, and it had a very deliberately provocative title, Is the Climate Warming or Cooling? And what was happening was there were people going around saying, climate change has stopped. Lord Monckton was lead among these. Apparently isn't really a lord, but what they did is they started the temperature counting from this point, which is 1998, which was the hottest El Nino ever. And so obviously in the years following the hottest El Nino, the global temperature is going to be negative, going to be less. And I might have expected that on average to go about 5 years. It went about 10, 11. This has been, I call it the so-called hiatus in warming. There's a recent paper by Tom Carl, which was in the press because it was attacked by Lamar Smith, the chair of the House Science Committee, that suggested that actually the hiatus didn't last as long as originally was thought. They found some errors in this kind of temperature record. So climate change is neither uniform in space nor uniform in time. And so we expect that that 1 year is not going to be warmer than the previous, or even that 1 decade may not be warmer than the previous, like you see in here. And this may be because of some changes in human activities, or it may be just changes in natural variations, like El Nino, for instance, or other modes of variability of the climate system, or combinations, which is what it appears to be for the most recent hiatus. This particular post-war decline is one of these things. It's a combination of things, but the human cause is the post-war industrialization, which the economy boomed after the war, and what that did is we burned a lot of coal and oil, some of which had sulfur in it. These sulfate aerosol pollutions, like acid rain producing stuff, tends to be reflective and have a net cooling effect. So it's an interesting thing. You have this short-term air pollution, which has like an average, these aerosol particles have a 3-week lifetime that tend to cool things, but underneath it you're increasing the carbon dioxide, which is a long-lived species. And so that's the explanation for this particular one. But I think the point really is that don't expect that it gets warmer at a linear rate. I mean, it's going to have wiggles in it.
We'll take our questions out to the hall. Let's thank our speakers.